Thank you very much. First of all, it's really, of course, a great honor and a surprise that I can be here. And thank you very much, especially for Dejan Popovic and Lana Popovic for inviting me to this beautiful day into this beautiful building. It was planned when we met a few months ago in Budapest, and I'm very, very happy being here in Belgrade. My talk will be a little bit different. It will be more theoretical, but not very theoretical. I will avoid equations, but it will be about modeling. So originally, I am a mathematician, and I came from a research institute for physics from the Hungarian Academy of Sciences, which is a research center for physics, but we have a small neurorehabilitation and motor control research group. I will talk about this work, what we are doing there, in the frame of synergies, but I will refer to Parkinson studies first, since it was the topic of the previous talk, and the next talk will be also related to motor synergies. So I will speak about synergies in a mathematical context, but I hope it will be useful for people with not mathematical background. As I don't have much clinical background, but I really enjoy this really interdisciplinary meetings. So how can I make a step here? Okay. Thank you. So, synergy, what is synergy? So, synergy means many things to many people in motor control. But synergy generally means that working together at a well-coordinated manner. People may work together to achieve a common goal, or muscles may work together at a coordinated way to perform a motor task, or even joints may work together. Coordinated rotations of joints may lead to a well-coordinated limb movements. But if something is wrong with the coordination or the cooperation between units, then the movement may not be performed well. So it's very fantastic that the central nervous system somehow can overcome this complexity of these multi-joint and multi-muscle systems and is able to control limb movements at a very nice, very graceful, very smooth way. So how can it be studied? How the number of controlled variables can be reduced to study the movement? Because if we are speaking about the muscular systems, we have many muscles, okay? And in the three-dimensional movement, like a reaching movement, we can represent it in a multi-dimensional space in which each dimension relates to one axis relates to one muscle activity. But we have many muscles. So dimension reduction methods may be applied to reduce the controlled variables, because muscles and joints are not controlled independently, of course. So classical method for dimension reduction is the principal component analysis. I will not speak about too much about this. I will speak a little bit more about non-negative matrix factorization, which is recently used, very widely used in studying muscle synergies. And it's an uncontrolled manifold approach, what I will also talk about, which is a study, an earlier study that I made with Professor Slobodan Jaric from the University of Belgrade and Mark Latash. I will refer to this later. So first I speak about the drawing movements of Parkinsonian patients, and then bimanual reaching movements of able-bodied healthy participants, and finally about arm cycling, which is our main present study. So about the Parkinsonian movements, of course, even young, famous people were affected by this disease. And here I am speaking about arm movements, not leg movements, as it was in the previous talk. And this is, for instance, a test that medical doctors may perform to examine the patients. Or the other thing that is very commonly used, drawing movements. They ask the patients to make drawings. So now we studied the drawing movements of Parkinsonian patients. The task was to track a figure. The figure was a square or a triangle or a circle, like here. And we recorded the joint coordinate, or the coordinates of anatomical points on the arm, and we computed joint rotations in the elbow and the shoulder. So They repeated the movements many times, and we studied the variance of the movements in the external space and in the joint space. The question was that what is more affected, the variance of the hand movement or the variance of the arm movement? The variance is very important if you speak about synergies later, because the variance may be explained by muscle or joint synergies. So what we can see after the drawing is not a huge difference, but you can see the Parkinson, this is one Parkinson subject and a control subject, how different are the 7 circles and squares, what they draw by the dominant and the not dominant hand. But this is very qualitative. So how can we quantize this? To do that, we represent the movement in this four-dimensional joint space, where each of the axes relate to these angular changes: shoulder abduction, adduction, rotation, flexion, extension in the elbow, and supination, pronation. So we represent the movement in by a four-dimensional vector, and then we compute the variance, the motor variance, first at the hand position, the head variance. This is a function of time, the hand position, and this is, I don't go details in the equation, this is simply we compute the average of the circle, the trajectories, and the square, the mean of the squared deviation of the individual triangles from the mean. This is the hand position variance, and we also can compute the variance of the arm configuration. This is the joint angular position variance with a similar simple mathematical equation. The only difference is here we have position in the three-dimensional or two-dimensional space, and here we have a joint angle with a multi-dimensional, in a multi-dimensional joint space. So the question was, which of these are affected more by the Parkinson disease? And here are some results. Here you can see the normalized time. The movement time was distributed into 1,000 equal time steps, and in each time step we computed the variance of the movement. So if there is a circle, they always started from the same position, ended at the same position, but during the movement the variance changed. And it was, of course, higher for the Parkinson patients. This is the red line is the Parkinson variance, and the green one for control patients. This is the average of many participants. And we can see what we expected, that the variance for the Parkinson patients will be higher. And we computed the average variance across subjects for different conditions, circle drawing by dominant, non-dominant arm, or square drawings. And in each case, we computed the mean endpoint variance, or hand trajectory variance for the Parkinson and control patients. And we computed this ratio because we wanted to know that how much higher is the Parkinson variance compared to the control in the hand position and in the angular configuration. And interestingly, there was no significant difference between these ratios. It means that the Parkinson's variances increased by the same rate in hand position variance and in arm configuration variance. What does it mean in terms of synergies? So if there is a healthy joint configuration variance, because of course we can never repeat a movement twice in our life exactly the same way, but generally the variance is small in the angular variance and the endpoint variance also, and especially if the synergy is good. The synergy means the cooperation between the joints. But if the arm configuration variance is increasing, this is multiplied by a constant here, which is greater than 1 in the Parkinson case. And here also there is a constant which tells us that how much higher is the Parkinsonian variance compared to the healthy. Then if these two numbers are very close, then we assume that the problem in the movement, in the coordination is not in the synergy, but in the individual errors in the joints. And the error compensation is still working well. But it also happens, it may happen that one of these constants are higher. For instance, if this D is higher, it means that the endpoint variance is much more affected than the joint configuration variance. Then it means that the synergy went wrong. So not only the individual errors in the joints, but the cooperation with the joints was also wrong, and this increased the variance of the hand position. So in all studies, the conclusion is that synergy was not bad. The synergy was good for the Parkinsonians, but of course this is an indirect conclusion. And the higher variance of the Parkinson patients was not the insufficient intersegmental compensation of joint errors, but the individual errors in the joints. We can argue against or for this, but this is what we found with our studies. So now I go back to the bimanual pointing arm movements, what I mentioned already, what we made with a Swedish group and Professor Jozsef and Laczko. Here, the task was that in the left arm, the participants had a target, and in the right arm, a pointer. And the task was to reach the target by the pointer. Again, they repeated the movements many times. Here, we represented the movement in a six-dimensional joint space. Here we had it was a planar movement. In the shoulder, elbow, and wrist, we measured the angles in both arms. And then we also computed the variance of the movement when they made it many, many times. And they practiced it for 1 week, and during the practice, we were interested if the synergy or the variance is improving or not. So this study related not to a neural disease, but the effect of practice or training. So here you can see that the variance, these are the black holes. These are, again, in a function of normalized time. Pre-test means before practicing the movement, the variance was much higher than after practicing. So the practice had a good effect on the variance. But what variance? Because there is the structure of variance was interesting. And this is the only mathematical equation that I write here, that there is a relation between angular changes in the joints and the change of the position of the endpoint of the arm, or in our case, the change of the distance between the pointer and the target. The question that how this distance can be stabilized during the movement. I mean, the distance is changing because it is getting to zero, but by repetitive executions, how stable is this movement control? And here, it may happen that there is a change in the angles in the joints, but there is no change in the hand position. And mathematically, these combinations of joint angles define a well-defined set, and this is the so-called uncompensated manifold, which means that if somebody makes angular changes in the joints in such a way that the endpoint of the limb remains stable, I can put my finger in one point and do many things with my arm. So we are looking for this set of angular changes, because if there is a variance in this subset of joint rotations, then the movement execution is still successful. That's why we defined the compensated variance, which was originally defined by Gregor Schöner and John Scholz. And for this movement, we computed the so-called compensated variance, which is inside in this subset, what I mentioned, and the uncompensated variance. The uncompensated variance means that there are angular changes in the joints which affect the position of the hand. So, which doesn't affect the position of the head, is called by good variance. This name is by Mark Laczko. I prefer the compensated variance, but maybe good variance is more understandable. At bad variance, when the joint rotations result in error in the movement of the hand. So the total variance in the joint space is the good variance and the bad variance. And if we divide by these two, if we divide the good variance by bad variance, then we get something which represents the synergy, that how well the joints are working together to perform a task successfully. So this is, again, a dimension reduction method because this good variance, this uncompensated variance is happening in a smaller subset of the set of all possible joint rotations which may execute the movement. So this is the final finding of this study, that after practice interactingly, the uncompensated variance decreased more. The compensated variance decreased more, so that variance, which didn't affect the movement execution anyway, which is a little bit counterintuitive, but it may relate to some optimization of multi-joint movements. So what I want to say here that it is well seen that this one special set of joint rotations include most of the variance of the movement, and this variance can be decreased by practice. So, and this is what I told you, this is what we concluded, that the good variance and the bad variance is divided by each other. This is a synergy index. Some people define the synergy index at a different way, but this index anyway represents, if this is very big, that it means that the variance in joint rotations is big, but still the movement execution is very good. But if the variance in the other space is big, which is orthogonal mathematically to the uncontrolled manifold, then the synergy, the joint coordination is not good for that particular task. So, and this is our present study with arm cycling movement. So here, today I was speaking only about, until now, only arm movements. Here we recorded not only joints, but joint coordinates, but EMGs of biceps, triceps, anterior delta and posterior delta muscles in both arms during arm cycling. Why arm cycling? Because in medical rehabilitation, this is a frequently used task, and we wanted to see, again, that first of all, the variance of the movement, and apply synergy calculation, which is the non-negative matrix factorization. This is what I will speak now about. So motor variance is computed from recorded EMGs. This is, for instance, in 10 cycles, how the biceps activity is changing. This is a nice periodic movement, but there are some variance in it. So we have 8 channel recordings here, and the question is that how good is this synergy, and how much can we reduce the dimension of the muscle space? First, I just represent you here that this is the movement in the external space. This is the hand trajectory, which is when the patient handled the crank, the handle of the ergometer. And then this is the trajectory on the left and right arm. And this is the trajectory in the joint space. Here I can represent the joint space because we have 3 coordinates, shoulder, elbow, and wrist angles. In the previous studies, we had more angles, so I couldn't make a graphical representation. You can see here that this is a periodic movement for both arms. This is an able-bodied person. So here, this is not an able-bodied person. This is a stroke survivor. This is for a bimanual cycling, and this is for a unimanual cycling. In the unimanual case, you can see that he needs more effort, and probably the variances of the joint rotations are much higher, and maybe the synergy, muscle synergy is not so good. So how can we formalize muscle synergies? And this is the non-negative matrix factorization that very briefly I try to explain, and many studies have been made with Professor Davalla, and Marco also may know more about these studies. And here, the main meaning is that we have many channels. Let's say here we have 4 in one arm or 8 channels in the 2 arms, EMGs. But we don't want to control all of these muscles independently. How can we reduce the number of controlled variables if we want to make an artificial control? Or maybe the brain also, the central nervous system, also reduces the controlled variables. But how? So here, this is a matrix where these are the channels, the recorded channels, muscle activities. And P means the time. This is the time, which means we have a very long matrix, tens of thousands of numbers, depending on the length of the movement. And we make a decomposition of this matrix. And for instance, in the arm cycling, we found two synergies. This two synergy means a time-independent relation between muscle activities. These are stable link between muscle activities. And this may be called as a module. And then this is the coefficients which are changing in time, like muscle activities. But the issue is that this original matrix can be reconstructed by linear combinations of two synergies. These are only vector with four numbers, like the number of channels, but we have only two of this. And if we multiply these two matrix, then we may reconstruct the original signal. If we can do so, then it means that we may reveal a fixed combination of of muscle activities, and these fixed combinations are combined by these coefficients during a movement. Here, for instance, this may represent a muscle synergy. These are four muscles, let's say 1, 2, 3, 4 coordinates of this first column here. And this is only the relative contribution of each muscles at that moment to this, at each moment to this movement. And this is another synergy. And instead of controlling four channels independently, we may be able to reconstruct the movement to control only two channels or two variables. And we were able to reconstruct the movement by two synergies in such a way that more than 95% of the variance of the total muscle activities were explained by these two synergies in many different cycling conditions, unimanual, bimanual, with different crank resistances. So this is a very strong, let's say, synergy that we could reconstruct the movement. And here is the reconstruction. The blue lines are the originally measured EMG activities of four arm muscles, and the orange lines are the reconstructed activities, and this reconstruction used only two synergies, so we controlled only two variables. And for the biceps and delta anterior, we had a very good alignment. For the triceps and the posterior deltoid, not so good, but still it is about 95% of the variance is explained by two synergies. If we are cycling by one arm. By two arms, we had 8 muscles, and 8 muscles could be reconstructed, activities can be reconstructed very well by 3 synergies. By 3 synergies, 95% of the muscle activity variance can be explained. And here we represented also that 4, 5, 6, 7, 8 synergies may represent more. Of course, by 8 synergies, when all of the muscles are independent, then 100% variance can be explained. So the main meaning here that applying, for instance, these non-negative matrix factorization methods, we are able to reduce the number of controlled variables. The question if, and I just participated in a meeting that was organized by Lee Miller a few weeks ago about the manifolds. What about the brain and the manifolds? These are only mathematical constructions, or in the central nervous system really are wired something like this, that a smaller number of variables are controlled in such a way that, a huge redundant system can be controlled. So this was about arm movements, and this is the last slide about arm movements. Here are these 3 synergies that I mentioned. So these are not EMG, not individual muscle activities. These are the timing of the time-dependent coefficients of 3 synergies. And by these 3 coefficients, by these 3 channels, variables, we can reconstruct the movement very well. This may be applied in not brain-machine, but body-machine interfaces when we record the EMGs and we make a dimension reduction and we control a movement. Let's say in the 3 dimension, we make a movement of a point by measuring 8 or 10 channels EMG and reducing the dimension to 3. This is maybe a very useful method for, I wouldn't say brain-machine interfaces. We are working on body-machine. Body-machine means that we get the signal from the muscles or from the joints. And this is finally a very simple synergy, but it is also a synergy that how biceps, triceps are working together in this arm cycling movement. This is the crank angle from 0 to 360, and we define the activity intervals of these muscles on that way that if it is above the 35% of the maximal isometric contraction. In this case, we have a co-activation interval sometime, somewhere, and this is just a very simple example. Why I show you this? Because this is the method how we defined muscle activity patterns for functional electrical stimulation. We made it also for upper limb movements for spinal cord injured people, and hopefully we will have it very soon in Hungary at the National Institute of Medical Rehabilitation. What we have now to make it for lower limb movements, and Professor Popovic and Anna Popovic have seen it in our institute a few weeks ago, and I know that you are doing similar methods, maybe by different stimulation patterns, but it would be nice to continue something like this together. And this is a stimulation pattern where we use two channels for each limb, quadriceps hamstring stimulation, and here we stimulate 3 parts of the quadriceps separately. So our long-term aim, and I have some results, but I don't show it yet, that we measure the EMG from the upper arm and try to use these EMG patterns to control the EMG channel for the lower arm. So if we measure 8 EMG on the upper arm and we want to control 2 channels in the lower extremity, we may be able to provide a new stimulation pattern. So this work was done by a small group a very small group in the Neurorehabilitation Motor Control Research Group at the Hungarian Academy of Sciences, and we continue a fruitful cooperation in this functional electrical stimulation field with the Medical University of Vienna, with Professor Meyer, and I didn't show the tricycle, but I hope to do the tricycling movement also. And I would like to express my thanks to the Rehabilitation Institute of Chicago, to Professor Muszaiwadi, who are working with this body-machine interface, and I am partly involved in this study. But I think the time is almost gone, or maybe even more. So I don't tell you more. Thank you very much.
Thank you very much.